So this lecture will talk about the rule that I'm going to call biconditional expansion. We're going to abbreviate that with just the letters BE. And this is a rule that's not in your text at all, although it's in a lot of sentential logic rule sets. We don't happen to have a version of this. And you might think we almost don't need it because of our rule of biconditional introduction and our rule of biconditional elimination. This rule is often what takes the place of those rules. But there's certain times when it would be still useful to have this rule. So I'm going to add it to our rule set. And if it comes up and is useful to you, then you can use it. So recall that when we were talking about the biconditional, we said, well, P if and only if Q is really just a shorthand way of saying if P then Q and if Q then P. And that's precisely what the rule of biconditional expansion does. It lets us move from the shortened version of the biconditional, P if and only if Q, to the expanded version, if P then Q, and if Q then P, and vice versa. So how is this rule useful? Well, there's a couple situations in which it might be useful. So I'm going to talk about some of them. So suppose you have the formula P if and only if Q in your argument. And suppose you'd really like to have the formula P arrow Q. Now you could obviously get this through an arrow in proof. And it would be easy. You would assume P, use biconditional elimination to get Q, and then you'd have what you need. But wouldn't it? It seems like it would be easier not to have to make an assumption for something that is clearly entailed by P if and only if Q. So with our new rule of biconditional expansion, we can have it much easier. Well, it's only like one step shorter, but it doesn't involve making an assumption and having to draw boxes. So it's easier in that respect. So we would use the rule of biconditional expansion to get P arrow Q and Q arrow P. That'd be by biconditional expansion on line 1. And then we could get P arrow Q by and elimination on line 2. So that's one way it might come in handy. Here's another way it might come in handy. So suppose we have the formula P arrow Q. And what we want is P if and only if Q. Now, we could get, and also suppose that it's going to be possible, well, we could get this through a double arrow introduction. We could assume P, try to get to Q, which would be easy using double arrow elimination. And then we'd have to assume Q and somehow get to P. And let's assume that's possible. Let's assume we have other stuff. We have other premises that will make this possible. Obviously, given what we have here, it's not possible. Well, we could do all of that, but it would be a little easier if we didn't have to do this part, because that's not really necessary. We already have P arrow Q, so if instead what we needed to do to get P if and only if Q was just assume Q and somehow use that to get to P, I don't know how many lines that's going to take. Which we're going to have to do anyway in the double arrow in proof. And then we create Q arrow P. And then we put these together to make P arrow Q and Q arrow P. And then get P if and only if Q by biconditional expansion. So we only have to do one subproof as opposed to two. So that's maybe a slight advantage sometimes. Okay, and then the final time it could come in handy is the real reason I put it in the rule set, because it turns out dealing with this is really kind of difficult. So if we have, suppose we had, without this rule, it's really difficult. So suppose we have a negated biconditional. Without the rule of biconditional expansion, we have no way to deal with this formula. We can't really do much of anything with it. Now, there are ways that we can work around it, but they're tough. They make for very difficult proofs. Whereas if we have the rule of biconditional expansion, we can do the rule of biconditional expansion inside the formula here. So we get P arrow Q and Q arrow P. And all of that is inside the negation still. Now it's a candidate for De Morgan's because it's a conjunction. So we can De Morganize that. We get not P arrow Q or not Q arrow P. And now we have negated conditionals. So we can perform negated conditional on each part. So we could get P and not Q, or Q and not P. And so on. We can do, so we've gotten it into something that we can do a whole lot more with than when we started out on line 1. It's a lot easier to work with. Even though it looks bigger and messier, we can now sort of get at stuff and hopefully do something with it, depending on what it is that we want to do. So this is the most useful application of the rule of biconditional expansion, I think. That's where I would probably use it the most. And I'll probably give you a proof that I might give you a proof. We'll see. There's a proof that is a lot easier with this rule that I might give you to do. I haven't decided yet.